Hello, ladies and gentlemen. Thank you very much for meeting again in our section of batteries under our paper 2 in chemistry. We understand that this one is just an extension of our electrochemistry, but now in this case we have already looked on primary batteries, and now there is need for us to switch on to what we call secondary batteries. Already we have highlighted that our secondary batteries themselves, they can be recharged. That is, they can be used over and over again. And we have already said that they rely on a reversible chemical reaction, and this reaction proceeds in one direction while the cell is discharging, and in the reverse direction while the cell is being recharged. Right? And now to do this, we understand that the external energy source provides a charge voltage that is slightly higher than the EMF of the cell. The positive terminals of the charger and the battery are connected to each other, and so are the negative terminals. So what we are saying there is our positive terminal of our battery are supposed to be connected to the charger and our battery, and the same applies. Our negative terminals are also supposed to be connected to our charger and our battery. Then main batteries, they require chargers that adjust the voltage and current during the charge cycle in order to charge the battery without damaging it. So now let us look on one of the commonest secondary batteries which we have, which we call the lead acid battery. So let us look on what we call the lead acid battery. This lead acid battery is the one which you normally see in our cars. So this one, it can also be called the lead acid battery, but just we can also call it the car battery. This particular battery was actually invented in 1859. So this one was actually invented in 1859 by a French physicist called Gaston Plantin, right? So this one was actually a physicist from France, and he invented this particular battery in 1859. It is an old design, but it has not been replaced because it is able to provide the high current necessary to crank a car engine to start it. So remember, if you don't have your car battery with you, you can't start the car engine. So there is need for us to have this lead acid battery in order for us to crank a car engine, right? In each lead acid cell is a number of plates that are grades of a lead alloy. We have the positive plates, which we call our cathodes. So we have the positive plates, and these positive plates, remember, we call these are our cathodes. So these particular positive plates are packed with lead oxide. So these particular plates, they are being packed with lead oxides, and the negative plates, which we normally call the anodes, these ones are actually filled with lead. So these ones, they are actually filled with lead. But now in between them, we have a porous separator, and this porous separator, that is the porous separator which actually separates our negative plates and our positive plates. So this one separates the two electrodes to prevent the plates from touching. So these ones the polar separator actually prevents the plates from touching. Otherwise, we are going to get a spark if they are not separated. So there is need for these particular cathodes and the anodes to be separated. So in our lead acid battery, this one is filled with a liquid electrolyte which we call sulfuric acid. So when the battery is fully charged, the sulfuric acid has a density of 1.25 grams per cubic centimeter. That is, but now we know that the density of water itself is equal to 1 gram per cubic centimeter, right? And then it is sealed with lead acid. Sealed lead acid batteries have the electrolytes in a gel. So now, first of all, let us look on what's really happening during the discharging of our battery. And we want to see the half reactions which are taking place during discharging. We want to see what's really happening during discharging. So we have the half reactions which are actually taking place firstly on our anode. So let us see what's really happening at the anode. So we want to see what's really happening at the anode. So at the anode, electrons are released and the plate becomes negative. Effectively, we see to it that our lead solid itself is going to be converted into lead 2 plus aqueous plus 2 electrons. And remember, we are at the anode, so this one itself is an oxidation reaction. As you can see, we are losing some electrons there. So if we are losing electrons, that one itself is an oxidation reaction. So we are saying that the lead ion combines with the sulfate in the sulfate ion of the electrolyte to form a precipitate of lead sulfate on the plate. So this particular lead 2 plus, which is being formed by losing the electrons, will now combine with the sulfate ions, and at the end of the day we are going to actually form lead sulfate. So we are going to have plus the sulfates ions. This one is a 2 plus in aqueous form, right? And then we are going to form lead sulfate, and this one now is a solid, but we are also losing the 2 electrons there, and the electrode potential for this particular reaction is equal to minus 0.36 volts, right? So in this case, sorry, here we have a problem there. We are supposed to have our lead solids combining with our sulfate ions, and at the end of the day we are going to have our lead sulfate plus 2 electrons, right? So now let us see what's really happening at the cathode. Let's see what's happening at the cathode. So electrons are absorbed and the plate becomes positive. Effectively, what we are going to form there is that we are going to have our lead 4 plus in aqueous form plus 2 electrons. We are going to have our lead 2 plus in aqueous form. Remember, at the cathode, this one is the positive electrode. Again, a precipitate of lead sulfate forms on the plates, and in addition, the oxygen of the lead dioxide combines with the hydrogen ions of the electrolyte to form water. So what we are having there is we are having our lead dioxide, which is in solid form, plus our 4H plus in aqueous form, plus the sulfate ions in aqueous form, right? Plus the 2 electrons